I don't know if it was, I know Sophie had some complaints about not exactly understanding summation notation.
I understand it now.
Okay, well, we get to learn a lot about it today.
Perfect.
Because as we work on writing Riemann sums as a summation notation, we have to understand a little bit more about it. So we actually go through and learn a little bit about it. So summation notation or sigma notation, because that is the letter sigma, yes?
It's Greek, right?
Mm-hmm. Yeah, this, what you guys are going to call the backwards E, the funny looking backwards E or whatever, that's sigma, okay? So it gives us a compact way to write Riemann sums into a single expression. This lesson will lay the foundation for the definition of the definite integral. And while you may have seen sigma notation in an earlier course, we're going to focus on using this tool to write Riemann sums. So, summation notation is a method for summing up a finite number of terms in a sequence, where the Greek letter sigma is the operator that indicates this process. Okay, so that backwards looking E that is sigma, what we call it in math is your summation notation or summation sign. And so this says the sum. Okay, this at the bottom, this is your lower starting point. So this is saying we're going to start at k equals 1. At top is your upper stopping point, and that tells how far you're going to, how many numbers you're going to plug in. Okay, x of k, that's what we're plugging it into. So that would be the sum expression, some mathematical equation that you are plugging into. Okay, now easiest way, let's go through number 1. Number 1 is very basic. Okay, evaluate the sum from k equals 1 to 4 of 3k minus 2.
What does it mean whenever it says evaluate?
Solve. Give an answer.
Did you just say
This was on my SAT.
what?
So we're giving multiple.
Okay, so first of all, k equals 1 is my starting point, 4 is my ending point. So what k values are we talking about here? K is what? 1, 2, 3, and 4.
Yes.
So we're going to do the sum of 3k minus 2 when k is 1, 2, 3, or 4. So we're going to plug in 1. We're going to plug in 2. We're going to plug in 3. We're going to plug in 4. And we're going to take those 4 values and sum them up. So add them. Okay, so I'm going to do 3 times 1 minus 2. That's kind of my first piece. Plus, what's my second piece going to be doing? So the first time through, whoops, I plug 1 in. The second time through, we're going to plug in 2. Plus, the next time through, I'm going to plug in 3. And plus, the next time through, I'm going to plug in 4. And let's do the math. So what? 3 minus 2 is going to be 1. 6 minus 2 is 4. 9 minus 2 is 7. And 12 minus 4 is 10. 1 plus 4 plus 7 plus 10.
Don't do that again.
22.
Stress me out. Do it again.
Okay. Are we okay with the basics?
Yes.
Because that is the very, very basics of how summation notation works. Okay? Obviously, ours are going to go beyond the basics. And we're not always going to be just, working them out. We're going to be using it more to express an answer. Okay? Consider the sum 9 plus 25 plus 49 plus 81. Choose all answers that apply.
Is there a shortcut to doing this, or do you just gotta do it?
I don't have a shortcut.
Okay.
In my opinion,
What do you think it is?
I did it yesterday. I was like,
in my opinion, you just have to do it.
Okay.
And now here's the thing. I take the first number, I plug it in. If it works and matches, then I plug the next number in, so on and so forth. If I hit a point where it doesn't match, I stop, X that one out, and move on to
I
another
think
one.
it's C or D because A and B only have 3 choices, right? What?
Okay. So the sum, if we look at this first one, from
No, B has.
1 to 3. If we want to get fancy here, why could I automatically rule out A?
Good job, Kylie.
Is that what Kylie was saying?
Yes.
We would be plugging in 1, 2, and 3, which is going to give me how many terms?
3.
3. How many do I need?
4.
Okay. Are there any others I can rule out for the same reason?
No.
No. Because 0 to 3 is 4 numbers, right?
Yeah.
Okay.
It's not.
So, I'm going to say I'm going to work here on B. And I plug in 0. If I plug in 0, 2 times 0 plus 3 quantity squared. So that's going to be 0 plus 3. 3 squared is 9. 9 works. Now I'm going to plug in 1. 2 times 1 is 2. 2 plus 3 is 5. 5 squared is 25. That works. Now I'm going to plug in 2. 2 times 2 is 4. 4 plus 3 is 7. 7 squared is 49. Now I'm going to plug in 3. 2 times 3 is 6. Plus 3 is 9. Squared is 81. Does B work?
Yes.
Should I stop here?
No. It says all of it.
No, because it says choose all answers that apply. Not a typical AP question, but okay, I'm going to plug in 1 down here because it tells me to start at 1, yes? 2 times 1 is 2, plus 1 is 3. 3 squared is 9. Okay, that was 1. Now I'm going to plug in 2. 2 times 2 is 4, plus 1 is 5. 5 squared is 25. That was what, 1, 2. Now I'm going to plug in 3. 2 times 3 is 6. 6 plus 1 is 7. 7 squared is 49. Now I'm going to plug in 4. 2 times 4 is 8. Plus 1, 9. 9 squared, 81. Does C work?
Yep.
It appears to. Now I'm going to plug in D. 1. 2 times 1 is 2. Minus 1 is 1. 1 squared is
1.
Now, when you asked if I had a shorter way, this does shorten some things a little bit, doesn't it? In that, as soon as you see, it's only 3 values and I have 4 terms, that would rule that one out. And honestly, C and D can't both work. I mean, if you think logically. 2n plus 1 squared and 2n minus 1 squared isn't going to give you the same when they're both 1 through 4. That's not going to give you the same thing. So in all honesty, if we found C that works, we could have said that D doesn't. Now, the thing is, if you find D doesn't work, do we know C works? No, you still have to try it. But okay, again, this is getting us familiar with summation notation, right? Hopefully you're going to be more comfortable with it today than you were yesterday. So, it is acceptable to use any letter for the index of summation. Most textbooks will use I, K, or N. Be aware that some summation expressions may have other variables. So, for example, a summation from K equals 1 to 4 of 2 to the K, X to the 2K minus 1. What are you plugging numbers in for on this one? It's K equals 1, so we're plugging in our numbers for K. Does that mean they go in for X? No. And so you'll notice that this one that X is just part of the answer. Okay? So you're plugging in for whatever they tell you to plug in. This will help you understand how summation notation can represent Riemann sums for a function. The example down there that's kind of hidden. It's the summation from I equals 1 to 4 of f of x sub, is that an I down there?
Yeah.
X sub I, and that has an asterisk. Okay, so that is something you might see in a calculus level problem, and that x asterisk just represents some arbitrary x on any interval. Okay, it's not, I don't know, I guess I want to say it's not anything to stress about. But it's just some arbitrary x there. Okay, so that would be the idea that you would have to be defined, what is f of x? What is my function? And then you could plug in based on the situation. Okay? And again, I'll be honest, we're not going to actually do a lot of plugging in. It's more about understanding how they work. So, okay, example 3. Writing a Riemann sum in summation notation. So, for the function y equals square root of x, draw rectangles, so this is part A. Draw rectangles forming a right-hand sum with 6 equal subdivisions, n equals 6, on the interval a to b equals 1 to 4, where the width of each rectangle is delta x equals b minus a over n. Huh? What'd you say? Well, but, so, okay, so n is 6 in that we need 6 subdivisions, right? On what interval, though?
0 to 5.
What's it tell me?
1 to 4.
On the interval 1 to 4. So we're going from here to here because that's what it tells me to do. Okay? Now, for the record, what is A and what is B?
1 is
A is 1, it's the beginning of the interval. B is the end of your interval, which is 4. Now, I don't know how mathy you're feeling. 1 to 4. It can be kind of obvious if you look. However, if your brain's not seeing it, can we use delta x formula here? What's the width of each going to be? B minus a divided by n. So subtract your endpoints of your interval. 4 minus 1 divided by 6. So that's going to be 3/6, which is 1/2. Are you saying, oh my gosh, because you weren't seeing it, or did you mess up the math?
did the math wrong.
So, does it make sense that each rectangle is a half wide when we want 6 partitions from 1 to 4? Because technically 1 to 4 is just a difference of 3, isn't it? Okay. Now, it asks us to draw rectangles as a right-hand sum. So I need 6 rectangles that are right-hand sums. So where's the first rectangle going to go?
1.5. It's the right side of it.
Okay. It's going to go from 1 to 1.5, and it's going to be the height of, it's going to be that height right there, yes? Because it's a right-hand rectangle. It's right-hand sum. So when we draw this first rectangle, are we okay with the first rectangle being like that? Notice I made the point showing you that that is where the right-hand sum is. 5 more times. So from 1.5 to 2, the right-hand edge of that rectangle, we're going to touch the graph at 2. From 2 to 2.5, we're going to touch the graph at 2.5. That's the right-hand edge of the rectangle there. And these are just barely above because of how the graph is, right? Am I making sense here?
Yeah.
Yeah.
Hannah, are you with me? I'm not convinced.
I'm trying to see too.
I'm following, sort of.
Okay.
Not like all the way there, but I'm like most of the way.
Okay. So I'll slow it for a moment, make sure. Okay, so my next rectangle, each rectangle is a width of a half, yes?
Yeah.
Yes.
So my next rectangle is going to go from 2.5 to 3. Like those are my sides. Because it's a right-hand sum, between 2.5 and 3, the right-hand edge is the 3. So my rectangle is going to be that height right there because that is where 3 intersects the graph. Okay. I'm just trying to make sure we get it, okay? So, and when I draw a right-hand sum, I guess you think about, you put your graph on the right-hand edge, or you put your rectangle, the right-hand edge of the rectangle on the graph, and then you're drawing the rectangle left. Okay. 2 more. Okay. Now, for going forward, what was our function here? Y equals square root of x, or I'm going to rewrite this as f of x equals square root of x, right? Okay, did I get everything I have here? I think I did. This was A and B. Okay, we're there? Okay, our goal is to find a general expression for the area of the kth rectangle. Okay, A of k. With that in mind, okay, in order to find the area, okay, of the kth rectangle, I guess what, okay, so realize we haven't defined A of k yet, have we? We don't have this formula yet. That is yet to come here. But the idea of we're going to have whatever our formula is of the first rectangle plus the formula of the second rectangle. The idea that we have 6 rectangles, right? So when it's saying A of 1, 2, 3, 4, 5, 6, it's referring to the 6 different rectangles we have. Now, summation, that is the sum from k equals 1 to 6, because that's representing each rectangle of A of k. Okay, so that's just kind of a general expression there. We're going to put some more details here. Okay, we're going to kind of fill in some details. And what this is, because I believe is at the next page where they give us the procedure. Yeah. This is kind of walking us through the procedure of writing out the Riemann sum. So B takes us to the next step. The height of each rectangle is the function value at the right endpoint of the rectangle, denoted as x of k equals a times delta x times k. Find the expression for the height of the kth rectangle. I can't say that, kth. Basically what I'm asking you to do is we're trying to find x of k. Now, what do we know we can fill in there? Do we know A?
Yeah, 1.
A is where my interval begins, which is 1. Plus, do we know delta x? Delta x is the width of each piece, which is either 0.5 or 1/2, to each their own. Okay? Times k, which k is just k. It's representing the kth rectangle. Okay, we have 6 rectangles right now. K is not anything we know right now. It's just representing that we're trying to write this expression in terms of k, because k represents the different rectangles. Okay. About all I can do is clean this up and write it as x of k equals 1 plus 1/2 k. Or you can write it as 0.5 k. Or you can write it as k over 2. Just be aware they're all equivalent. Okay? So that is your expression for the kth rectangle. Okay? Are we okay with that piece? And again, this is a formula that when we get to the next page, this is part of your steps. This is a formula you'll just kind of need to become familiar with. Okay? C. Write the area of each rectangle, where A of k is the width times the height, which that's what the rectangles we've been doing are, right? It's the width of the rectangle times the height of the rectangle. Or, in other words, delta x times the function evaluated at each x value. Okay, so yeah, I know we think for area of a rectangle, we think width times height. But remember, delta x is width, and your height comes from evaluating your function at whatever value it is. So, in this case, what do we find this? A of k. What is my width? What is delta x? And I actually write it as 1/2, but then I actually do go to 0.5 just because it's easier to kind of what we're getting ready to do. Now, f of x sub k. I'm going to sidebar this. You can decide how much you need to write. F of x sub k means we're going to take x of k and plug it into f. What is f? Okay, so remembering that f of x is square root of x, yes? So f of x sub k, every place you see x, we're going to replace it with x sub k. Now, I'm taking extra steps here. So square root of x sub k. However, what did we just do in the previous step? Didn't we just find x of k? So the idea now is that f of x sub k, instead of saying x of k, what is that equal to? 1 plus 1/2 k. Are we there? Okay, so the width is 1/2. The height is the square root of 1 plus 1/2 k. That is your function that goes in your sum. Okay, if you prefer, and for whatever reason I switched at this point and I said 0.5 times the square root of 1 plus 0.5 k. Some of you had already switched, some of you don't care. I don't care what you do. Okay. That's your next step. One final step. That's actually to write the notation here.
You just have to plug it all in and
Pretty much.
add it all together.
Write the summation notation for this expression above for values of k from values of k from 1 to 4. Now, beware. Okay, we have to interpret what that means. So, summation notation. That means I'm writing. Oh, wait, I need room. Are you laughing at my sigma?
Donna's.
Oh, I didn't leave room to write above it. Ugh, I give up. Okay, we're just going to go with it.
We have to write that?
You have to write a sigma, yes.
They're not that hard to write.
I would harass you about it, but Mario was the one picking on me, not you. So, I mean, it is what it is. Okay,
Okay, that's not.
now, it says
Mine are weird.
That's pretty good.
Yeah,
for values of k from 1 to 4. And that's, okay, so when it's saying for values of k from 1 to 4, realize right here, 1 to 4, those were my x values, right? This, here's what, let me tell you what this is not. This is not k equals 1 to 4. We took that interval of 1 to 4 and we broke it up into how many rectangles?
6.
6. So we're going to use k equals 1 to 6 because 1 to 4 are not k values, those are x values. That's your interval. Are we understanding the difference? Because when we do this summation, we're not summing up 1 to 4, we're summing up 6 rectangles. Okay? So there's your sigma notation. And then it's of, we just wrote the function here, didn't we? Because we're basically doing this right here. And so now it's going to be of 0.5 times square root of 1.1 plus 0.5 k. Okay. That is writing your summation notation. Okay. I didn't prep for this, so I'm totally going off of my notes. You can plug that into your calculator, I believe.
Ooh.
Yeah, you can.
And this is where I said I didn't prep for this. Mario may be teaching this section unbeknownst to him because he probably knows it better than I do.
Math zero.
I don't
Okay, never mind. Doug knows it better than I do.
I've seen
I have math 0 written down, or alpha F2 number 2.
Why does Emma still get her own calculator?
Because I haven't ripped your name off. I ripped Kinson's name off yesterday. I didn't think of, and that was only because someone said, "Ooh, I want Kinson's calculator." I said, "Are you telling me I need to take the name off?"
Does he not click anymore?
He does not.
No, he won't.
Okay,
Which makes sense.
so
Which
math 0 is what I have written down.
Oh.
So math 0, if you're in your math menu, 0 after number 9, because where else would 0 come? Summation. And notice it even has a little sigma, doesn't it?
You can't put the top number in.
Now, notice it says alpha there. So I think you could type in, you could actually use K.
You can. I used X because I don't.
Yeah, because, okay, so
Which
it was,
A?
when I brought it up, it was flashing, my cursor had an A on it, which means it was set up in alpha. K is the green letter above the left parenthesis.
Oh, you can just
Wait,
use
K is
use
what?
K.
Because, yeah, it doesn't mean anything.
A, B, C, D.
So I'm going to do K equals 1 to 6. And then I'm going to type in. Now, since I used K, I have to use K here, right?
Yeah.
0.5 square root of 1 plus 0.5. Now, to get your alpha, go to the green alpha. Notice it, well, it didn't flash alpha for me. It just was being weird there. But this should do it. Yes.
Okay,
One more.
did not feel like I got it right.
Take on the board, yeah.
4.9.
So it's math 0. It is up in your alpha F2 shortcuts. Okay, so math 0. As I said, Doug had already found it, but I had my note because I don't remember that from year to year. I use it like once a year. So 4.911 is what I'm going to say. Hey, while we're talking, what kind of estimate is this?
Under.
Over.
Over. Oh, it is over.
It's
Shoot.
barely over.
Sorry, guys. Barely over.
A small.
Very small over.
I did not use up any of that.
Well, in mine, it's normal here.
Yeah.
The problem is I'm just doing this all on one page. I didn't load it as 2 separate pages. And so realize when mine gets ugly up here, that doesn't mean it's ugly here.
Mhm.
Sometimes it does, but it just means it's harder to write on the big key. Okay. Top of the next page. It summarizes basically what that ABCD just took us through. Okay. So first thing is find the width of each rectangle on the interval. That's that formula that you're going to want to know. In order to find the formula, it's B minus A over N, or find the width. And that's subtracting your 2 intervals, or your endpoints, divided by how many partitions you want. And find the right endpoint of each rectangle. And that's because we're talking about right Riemann sum right now. Okay. That obviously could vary. Well, no, the right endpoint is not going to vary. Excuse me. It varies later on. So the right endpoint, which is that formula, right? That x of k formula that we talked about on part B, that's that. Okay, so you use that formula always. Find the area of the rectangle. So this right here was the step. Then finding the area of the rectangle, that's doing the delta x times the f of x of k. And then notice it says then right Riemann sum or left Riemann sum. For a right Riemann sum, which, I guess do I have this on the next page? What I will say, a right Riemann sum, that is what you are more likely to see. Okay, I'm not saying you're not going to see the right Riemann or the left Riemann sum, but in this scenario, you're more likely to see the right Riemann sum. Notice for a right Riemann sum, like what we just did, your k values are going to go from 1 to n. Okay, because it's the right hand and you're representing to the left. For a left Riemann sum, your values go from 0 to 1 before n. Okay, and the idea there, and I don't even know if I can express this well, but, okay, if you've got, there's your beginning, there's your end. We're pretending here, okay? For right Riemann sums, we would use what? We would use this one, this one, this one, this one, and this one. So thus, it's going from 1 to n. What about left? Left, we would start where?
With that one.
This one, and we would go up to, what's the run right before n?
1 and minus 1.
N minus 1. So do you see the difference? And that's the only difference there. K equals 1 to n, or k equals 0 to n minus 1. Okay? So that is not a great picture, but I think it gives a good explanation. It makes it connect. Okay, let's see. We should be able to get number 4 done. Use the procedure above to write the expression that represents the approximation shown below.
I can tell you it's not B.
Why is it not B?
That is not a whole number.
It starts at
Starts at 0.5.
Yeah. Is it going to start at k equals 0.5? No, it's not going to start at k equals 0.5, and because you can't, 0.5 to 4. Well, what am I plugging in then? So I think that is a valid piece of information that you could rule that one out.
It can't be D.
Yeah.
Oh my gosh, we're ruling everything out, not even writing it. But okay. Why not D?
It's a right.
0 to 5.
Yeah.
It's
Okay.
That doesn't make sense.
It's starting at 1.
So if we think about this, how do I want to, what kind of rectangles are these?
right hand sums. Or right hand sums.
Can we agree that those are that's right-hand rectangles? Okay. Because they are right-hand rectangles, the heights we'll be using will be these heights right here, yes? Will I be using this piece right here? No. And that piece would be represented as 0 because it doesn't matter that this is a k value, right? So this piece would be represented as 0. So we could agree here that that one's not going to work also because of that's 0 and we are doing right-hand Riemann sums. Okay? Now,
Can you put that into y equals?
well,
It's C.
let's go through with some pieces. Delta x. Thoughts on delta x, folks?
0.5.
B minus a over n. What are a and b?
1 and 4.
I kind of wrote over them here, but you have them, right? 1 and 4. So 4 minus 1. What is n?
6.
Because they already broke it up into 6, didn't they? 4 minus 1, 3/6, 1/2. Yes? And in all honesty, did we even have to use that formula? Can't we just tell that each rectangle is 1/2 wide? Sorry, my brain was thinking more the steps. Okay? Now, with this in mind, where do I want to go next? X of k. So let's talk x of k here. What you would plug into your equation is a, which what we say a was? 1, plus delta x, which is 0.5 times k, right? So this is going to be plugged in to some formula.
But we don't know what F.
We don't know a formula, you're right. But, and we can see it being plugged in here we can see it being plugged in here.
Oh, but this one has 1/2.
Yeah. So my next step is to delta x times f of x sub k. Well, delta x was already 1/2, or excuse me, I was using 0.5, wasn't I? 0.5 times f of x sub k. Well, I don't know what f is, but it's going to be f of plugging that 1 plus 0.5k. So because it has the 0.5, it has to be c. Okay? Trying to think, do I have anything else there? And because it's multiple choice, yeah, I guess in mine I actually worked on finding the equation there, but I think the 1/2 being there or not being there makes a difference too. Okay? And don't worry, we will get some practice actually writing our own. Yeah, so. Okay, bottom of this page. Let's see. Definite integral represents the area under the curve of a function. A Riemann sum gives us an approximation of that area. Imagine that we could create an infinite number of partitions or rectangles in a Riemann sum. The approximation would get closer and closer to the actual area as the subintervals in the Riemann sum increased. We can't take a Riemann sum with infinite rectangles, as in n equals infinity in our summation, because infinity isn't a real number. However, if R of n represents the right Riemann sum approximation within subdivisions, we can use limits when we want to take something to infinity. Then the exact value of the definite integral can be shown to be the limit as n approaches infinity of R of n. And so, summarizing there, we can get smaller and smaller rectangles, right? And we're going to get closer and closer and closer to the real answer. However, the only way you can get the exact answer is taking the limit as n approaches infinity. Okay, what answer is that approaching? Okay, so this is kind of what we're doing here. B minus A over n is your width, right? This is your heights. So this is the width times the heights of the rectangles. Okay, summation notation. We're going to talk next week about integrals, and that's exactly what that is. Okay, that's going to find us the area under the curve there. But right here, this is our Riemann sum that we're working on writing. Notice, if we put a limit as n approaches infinity in front of it, that's making it precise, okay? So what we just did, the summation from k equals 1 to n of f of x sub k times delta x. Okay? Okay. Is that where I'm stopping?
That's where mom stopped.
That's where you're stopping? Some of you stopped a while ago. Okay. Okay, yep. Definition of the definite integral, which is what I just feel like it was kind of doing on the other page. So we'll be ready to start example 5 on Monday. So here's the challenge. You have to remember what we're doing today.
That's actually not funny, so I would not touch it.
Please don't throw phones.
I already dropped my old phone in the hot tub.
I don't want to risk breaking phones that don't belong to us.
It belongs to
I think they're
John.
Mario's, right, Mario?
I would not recommend pissing off John. He's kind of scary.
He's only scary when he's mad, probably.
John.
Dad.
Hey, Dad.
Her daddy.
John.
It's like him.
I go with Dad.
Not daddy. Don't call me daddy.
That works around.
Oh, I should probably stop the recording.
I don't.
I'm gonna go.